This is the first generation Raspberry Pi, which came out back in 2014. It has a 700 MHz single-core processor and 512 megabytes of RAM. By modern standards, this is basically a calculator. But today we're going to see if we can push this 12-year-old hardware to its absolute limit by running a large language model on it locally. In this video, I'll show you which is the tiny model that you can run on a Raspberry Pi, and we'll see how it performs, and I'll show you how to install all the necessary dependencies so you can try it out for yourself. It's gonna be a lot of fun, so let's dive into it. Honestly, I didn't think it was possible to find a model lean enough for this architecture, but after some digging, I actually found a candidate. Meet the Falcon H1 Tiny. It's an incredibly compact model with just 90 million parameters. It was developed by the Technology Innovation Institute in Abu Dhabi, specifically to explore the extreme lower bounds of language modeling. But how could they make a model that small? Is there some kind of technical magic sauce behind it? Well, not really. They're basically using the same hybrid transformer plus Mamba architecture that companies like IBM used for their tiny Granite 4 models, which I also did a video on if you want to check it out. But here's the thing, to successfully squeeze this model into memory, we have to talk about quantization. Now, the Falcon models are available in 2-bit, 4-bit, and 8-bit versions. Now, you might be tempted to try the ultra-lean IQ or importance quantization, but here's the catch. Those newer methods rely on a complex bit manipulation that requires modern CPU instructions to be efficient. On our vintage ARM v6 chip in our Raspberry Pi, this won't cut it. So instead, we have to go with the old school Q4 models, which is the gold standard for our case. It uses a medium-sized legacy quantization method that the Pi's processor can actually handle without choking. It gives us the best intelligent per megabyte ratio while keeping the logic intact. But to get this model running on this first-gen Raspberry Pi is not a trivial task. Since the Pi uses the ARM v6 architecture, it lacks the modern Neon instructions that almost all of the AI libraries depend on. But luckily, there's llama.cpp, which we can use to run our inference. But in order to do that, we have to compile its binary specifically for our ARM v6. And if you would try to compile it directly on the Pi, it would probably take 18 hours for the compiler to finish. That is, if it doesn't crash from out-of-memory errors first. So to bypass that, we have to get a little bit creative. We need to cross-compile these binaries on our laptop beforehand by using doc-cross, specifically targeting the ARM v6 instruction set with the VFP math unit enabled, and then copy them over via SSH so we can get straight into inference. So that's exactly what we're gonna do now. So first we need to flash the leanest OS possible onto our Pi using the Raspberry Pi Imager. And for a board with only 512 megabytes of RAM, every megabyte counts. So I'm going to go with Raspberry Pi OS Lite, the 32-bit version, since it doesn't have a desktop interface and it idles at a tiny fraction of the memory that the standard OS uses, leaving almost all of our RAM available for the model to run. And here's another important note. Make sure to use the advanced settings to pre-configure your Wi-Fi and enable SSH. Because on these older boards, it's much easier to manage everything remotely, so you don't have to fight with that sluggish local terminal. Now, once the Pi is booted and we've SSH'd into it, we need to address the ARM v6 problem. So if we tried to compile llama CPP right here, the Pi would literally spend the next day and a half just chugging through headers. So instead, we're going to do it on a regular laptop to speed up compute and save time. So let's clone the source code of llama CPP and create a dedicated build directory where we will store our build that we'll be using on our Raspberry Pi. Now here's another problem. My Mac is using ARM v8, which is the 64-bit version, not the 32-bit ARM v6. And they have different instruction sets. So to compile binary specifically for the Pi, we need to use doc-cross, which is a cross-compiler toolchain that runs on my Mac but generates binary specifically for the Pi's legacy architecture. Next, we need to configure the build, and this is where we need to be extremely precise. So we need to pass some very specific flags. First of all, we need to turn off shared libs to create a single portable binary. And then we have to turn off neon because our Pi lacks those modern math instructions. And we need to disable OpenMP to keep our memory footprint as lean as possible. We're essentially stripping out every modern luxury to ensure the binary is compatible with our old school Pi board. And now if we hit build, in about 2 minutes, we should have a fully compiled, optimized llama completion binary ready to be copied onto our Pi board. And now I'll use SSH to connect directly to my Pi via the network and create a fresh directory on the Pi, and then SCP to copy our custom build binary onto it. And one last thing we need to do here, let's go ahead and download the 2-bit, 4-bit, and 8-bit legacy quantized models of the Falcon, because we'll be testing all of them sequentially. And then copy them to our Pi one by one over the network in the models folder. Now here comes the fun part. Let's move over to our Pi and execute our first inference test. We'll start with the most aggressive compression, the 2-bit quantized model. And here we need to run this long command. And basically what I'm doing here is prompting it with a simple hello, how are you, and capping the output at 32 tokens. And we're specifying exactly one thread because, well, that's all we have. And we're also keeping the context size tiny at 128 tokens to save every possible byte of RAM. But the most important flag here is no mmap. Typically, Llama CPP uses memory mapping to load models, which is great for high-end GPUs, but it's a nightmare for our Pi board. On a 32-bit system with only 512 megabytes of RAM, mmap can fail if it can't find a contiguous block of address space. So by disabling it, we force the model to load directly into the heap, giving us much more stable control over our limited memory. And with that said, let's run the command. And there it is, our first tokens. As we can see here, the 2-bit version is struggling a lot. First of all, we can see that it's processing a single token in like every 3 seconds, which is to be expected on an old Raspberry Pi board. But more importantly, the answer is just complete nonsense. On a 90 million parameter model, the weights are so compressed that the linguistic logic has basically collapsed. It's barely coherent, but technically, it is working. So now let's see what happens if we swap it for the 4-bit model. And look at that. Now we get a coherent greeting back. So that is a success. We now have an actual AI model running locally on the Pi and responding logically to our prompts. So yay. Now let's push it even further. Let's see if the Pi can handle an 8-bit model. And this time I'm going to ask it something more intelligent, like what is the capital of Albania? And well, that is just wrong, because the capital of Albania is Tirana, and that is clearly not factually correct. But if I ask what is the capital of Belgium, it responds correctly. So this is showing us something very interesting. It seems that the 90 million parameter crunch comes with its own cost. It might have accurate knowledge about larger, more popular countries, but lacks knowledge about lesser known countries and probably lesser known topics, and that is just the nature of knowledge. There is a finite amount of knowledge you can fit within those 90 million parameters. But nonetheless, the result is super cool. And this is a confirmation that yes, there are indeed AI models small enough and lean enough to run on a 12-year-old Raspberry Pi. Is it fast? Hell no. Is it precise? It might not be. Should you use it in production? Probably not, unless you want to build a very, very, very slow robot. But most importantly, now we know that it is theoretically possible. So basically that's all I wanted to prove in this video, and to be honest, this experiment was a lot of fun. So there you have it, folks. Those are the Falcon H1 Tiny models, probably the smallest AI models currently out there, and now we know that they are in fact small enough to run on a first-gen Raspberry Pi, which is super cool. I can't stop celebrating how cool this fact is. Although the practical implementation of it is useless, it's still cool. So let me know, folks, folks, if you have any funny thoughts, comments, or remarks about what you just witnessed, post them in the comment section down below. And folks, if you like these types of technical breakdowns, please let me know by smashing that like button underneath the video, and also don't forget to subscribe to our channel. This has been Andres from BetterStack, and I will see you in the next videos.